my research entails developing statistical computing and machine learning methods for fitting complex, massive data sets, identifying risk factors, and making predictions for practitioners to use for real-time risk assessments. So the focus of this work is using statistical theory to develop computationally efficient methods, automated methods, and output inferences to be used in scientific problem solving. So one goal of this talk is to give you a feel for what is statistical computing, what is machine learning. And I'm going to start this with a bit of history and a lot of pictures of computers. So I feel like I came into statistical research at a really exciting time, as my career has kind of coincided with seemingly a continuous explosion in computing power over the last 3 decades. Where did the clicker thing go? So many papers up here. Does this work? Yes. So I first learned how to code in 1981 on this deck writer. And I see some smiling faces. Some of the older folks, yeah, Marie recognizes this. So this is a hard copy terminal. Everything you typed was printed on the paper. Everything the computer outputted was printed on the paper. The infamous spooled paper, right, with the perforated edges that you tore off. So we wasted a lot of paper, unfortunately. But very soon after this, I went to a junior senior high school. They were able to get funding for a whole lab's worth of these infamous green screen monitors. All right, so this is the Commodore PET machine, which I think a few of you have worked on. And then by the mid-1980s, I'll say it wasn't uncommon for people to have a machine at home. All right, and so the Commodore 64 was the popular one. So that's what my parents bought me. So you still had this massive CRT display, still had a dot matrix printer with the spooled paper. But what I want to point out, I don't know if it's very clear on here, but there's a floppy disk drive behind me there. So there was no internal hard drive, very little memory. And so my point here was, even as a junior and senior in high school, for computing tasks, I had to write data to disk, read data from disk, and it was really slow. All right, so what I'm going to argue here is that in the 1980s, statistical computing, quote unquote, entailed doing a lot of the mathematical approximations to make the computing easier, right? So it can easily compute. And I want to show you kind of one of the popular approximations. Whoops. I was testing this out earlier, so it's not at the beginning. One of the approximations that we use even to this day, the essential limit theorem. And I'm going to leverage this demonstration to introduce some data that I'll be showing later. So this is visits of Introstat students here at SDSU to the Math and Science Learning Center, which is a tutoring center on campus. And so what you should notice is that, unfortunately, a lot of students don't take advantage of the Learning Center. So there's this spike at 0. There's this group of students, a pretty good group, who go 1 to 3 times during the semester. But there's still a good group of students who go once a week, if not more. All right, so for this demonstration, the main point is that we have what's called a skewed distribution. All right, so we have a spike at 0 and then this long right tail. Now, if I was to collect multiple data sets, all right, so say for multiple semesters, multiple courses, but what I'm going to do is run a simulation. So I'm going to resample this data to mimic the idea of replicating my data set. And I'm going to count or compute the average number of visits to the Learning Center. And it turns out that over multiple data sets, right, as I collect more and more data sets and compute this mean, the distribution of these averages approaches the infamous bell-shaped curve, the normal distribution. All right, and so this is the central limit theorem. I see Professor Velato shaking his head. He probably showed it in class a couple weeks ago. So the point here is that the central limit theorem has been around for hundreds of years, right? So models, inferences that are based on this normal distribution are really well understood, okay? And so in the 1980s, what we were doing, well, I wasn't part of that, but statistical computing entailed identifying a central limit theorem, deriving mathematical approximations based off of the normal distribution to easily compute inferences, okay? All right, so Now we're into 1990s. So I served as an actuarial intern, summer intern in 1990. That's my cubicle. The Equitable Life Insurance Company in New York City, for what it's worth. This is an IBM PS2, right? Significant advancement in computing power. All right. Still have a dot matrix machine. You can't really see it here, but there's actually a hard drive sitting on the floor. All right. And in fact, in the cubicle right next to me was a networked machine, right? That was shared by everyone on this part of the floor. But nonetheless, we were able to get to databases. We were able to do some more high-powered computing. And so as we headed into the 1990s, statistical computing, right, we were able to do more computationally intensive methods. And in fact, the hot topic of the time was repetitive simulations. All right, and in fact, that's what I did my dissertation on. So this is a picture of me in the summer of mid-1990s, graduate student at Cornell University. I like this picture because, notice, lots of books. No computer on my desk. So most of the graduate students did not have computers. There was a lab on the other wall that had 3 pretty powerful IBM machines, so we could do some significant computing, shared among 10 graduate students. Actually, the joke I was going to have here is I'm sitting here at Cornell University wearing a Yale t-shirt. But the other thing is that there was internet, but it was still dial-up. And in fact, those machines, we were still dialing up to get on the internet. So we were still reading books. There was a library right across the hall with hard copy journals, right? We weren't downloading articles, right? We were still reading things on paper. But by the late you can't even see this, but this says 1997. By the late 1990s, I had graduated, and I was a visiting scientist at the National Center for Atmospheric Research. And Professor Bailey, Professor Bailey, who's a colleague of mine here at SDSU, she was also a visiting scientist at NCAR. And we each had sun stations on our desks, all right? And it's hardwired. I don't know if you could see this wire. So massive computing power, right? So we were able to do some of these repetitive computational tasks. So in the 1990s, what we did is we used our understanding of the data structure, right, probability distributions, to build up simulation routines for drawing inferences. And I put some of the keywords up here. So MCMC is Markov chain Monte Carlo. Fancy word, but Markov chain is just, it's a probabilistic structure, right, for us to build up our simulations. And these were called Monte Carlo methods, Monte Carlo inferences, named after the Casino de Monte Carlo in Monaco, just because we're using chance events, right, to do these simulations. This was my dissertation research. The bootstrap was another popular method, and in fact, that's what I was doing for the central limit theorem demonstration. So it's this idea of resampling your data over and over again with replacement to replicate the data, right? And from that, you can build up a sampling distribution, you can get confidence intervals, et cetera, for those of you who know about that stuff. Smoothing was also very popular. Smoothing is not really simulation, but the idea of doing repetitive simulation to identify patterns and trends in your data. All right, and so what you do is you successively subset your data up. You actually fit regression models and smooth your data, right? Look for patterns. Okay, but the point here is that we're now having the computer do the approximation work through simulations. All right, and Dr. Rong Zablocki is in the audience. So she was my last PhD student, her to do MCMC. So she, part of her dissertation was developing Markov chain Monte Carlo techniques in bioinformatics. I love this stuff. I spent half a career doing it, but unfortunately I don't have time to go into any more detail on that today. I want to focus on machine learning methods. All right, so that'll be the focus of my talk today. All right, so we're now moving into the mid-2000s, late 2000s. This young man is sitting in my office at SDSU, still have a sun station, narrower monitor, an even more powerful IBM PC. I don't think that was an IBM, but it was a PC. I like this picture. So this is a picture of my colleague, Professor Fan, who's also my wife. But she's in statistics here at SDSU. She also has a sun station at her desk. But I want to point it out, there's this massive laptop that she has. It's hardwired, But we wanted to do heavy computing on the road, right? So we had these really thick, heavy laptops, but we were able to do it, right? And so the hot topic in the 2000s, and definitely heading towards modern times, was machine learning, all right? So next illustration, I want to show you a machine learning technique. So a number of you might be surprised you have actually been exposed to machine learning, whether you realize it or not. And a lot of you have used machine learning techniques in that basic linear regression is a simple and foundational machine learning technique. All right? And in fact, it's the foundation for many of the more advanced tools that we use to this day. So again, I'm going to leverage this example to introduce some data I'll talk about later. So this is now final exams in our Intro to Stat course. It's out of 300, and we're looking at the relationship between final exam score and an algebra assessment we used to give at the beginning of the semester just to gauge students' mathematical proficiency coming into the course. All right? This is now part of the middle school curriculum, right, where we talk to kids, well, not we, I'm a middle school teacher, but the teachers, God bless them, teach them how to look for trends in scatter plots. And definitely by high school, AP statistics, college statistics courses, we teach them how to find a best fit line to a scatter plot. I'm only showing you a subset of the data here just to make it more accessible visually. But the whole point here is that I'm trying to find a best fit line to this data. And what I do is I look at the distance between every single data point and the line. So that's what's represented by these vertical lines here. All right? I do that for every single data point. So how far is each data point from the line? I take the average of all those distances, and the one line has the smallest average distance is the best. Okay? And so for this data set, it turns out to be this one. Now we can make predictions, right? So that's what these open circles are. Right? So here's a student who scored about a 73% on the algebra assessment, and we would have predicted them to score about 200 on the final exam. They outperformed it. Here's a student who unfortunately underperformed. They scored about 80% on the algebra assessment. We would have predicted them to score about 220. All right? And again, they underperformed. But the bigger point here is that we now assume that each of these errors are normally distributed or approximately normally distributed. And so we can assess our confidence in these predictions through confidence intervals, prediction intervals, for those of you who know that stuff. All right? Now, I mentioned regression models are kind of the base machine learning tool. And part of it is because they have very strict assumptions. And I'm going to mention just two right now because we'll be using them later. One is that, well, for one, we would never fit a model with one variable in it, right? Here, just algebra assessment, right? There's other metrics we have on these students. Some of those metrics actually will impact the effect of algebra assessment on the final exam score. For example, we have a course dedicated towards business students for intro stats, right? And so this trend line might be different for business students than other students. If you took calculus before, you probably would have a different trend line. All right? This is called effect modification. And so you have to account for that in your models. The other thing is there's going to be correlation, right? Most of these, or I shouldn't say most, but a lot of these students are first-time freshmen. So we would include high school data in these models, right? High school GPA, performance in high school math courses, maybe how many math courses they've taken previously. Obviously their major, whether they've taken AP Stat, AP Calculus, so forth. All right? Well, AP Stat, hopefully not, though I think a lot of students do it just to get an easy A. But anyway, the point is that these are all correlated. And this regression line fit is really not going to be impacted by the correlation, but our uncertainty, right? These prediction intervals are going to be affected. Okay, so the more advanced models and machine learning tools have to account in some way for correlation between all these variables. All right, but the take-home message here is that the machine learning techniques really, I think of as having two goals. One is to look at the relationship between an output, here final exam score, and an input, here that algebra assessment, and then make predictions of the output based on the algebra assessment. Okay, so I call these, and this is a term that's been introduced in the stat literature at least, attribution and prediction. Okay, so let's move on. Now we're into modern times. All right. So this is a picture of Dr. Guarcello's lab. With Dr. Guarcello, I'll talk more about her later. So these are two of her interns from this past summer. I don't know if you can easily see it, but they're on Mac laptops. There's a Mac lap. Actually, Dr. He is in this picture. Actually, I think that's Josh. Where's Dr. Beamer? Yeah, so he's in the corner there. I'll mention them later also. But anyway, these are laptops. Oh, there's Jeannie. These are laptops which are major computing machines, probably more powerful than the Sun Station that Professor Bailey and I used, right, at NCAR. So we can do a lot of computationally intensive methods. We now have a laser printer. The double monitor, that's the popular thing at Dr. Guarcello's desk. This is a picture of our Data Champions program, which I hope to have time to talk a little bit about later. This is at one of our active learning classrooms on campus, where we can have students, or in this case, data champions, in pods around a computer with large screen monitors, right, where we can project the computers and discuss and collaborate on stuff. All right, and of course we now have generative AI, and the statistical viewpoint on this is that we're collecting a lot of data, right? So I mentioned wearable medical devices, which is almost continuous data on people. We have streaming online data of text, images, right? And so I would argue that machine learning research these days is aimed at constructing, optimizing, automated algorithms that can handle more and more data, more and more complex data for drawing inferences. Okay? All right, so that's our history lesson, if you will. All right, so what I want to do now is talk about three applications of where I and my team machine learning techniques, primarily in learning analytics, right? Because that's been the topic I've been working on for about the last decade. I'm going to start off with what I think is our most successful story, admission modeling. And I'm going to show you two things. One is kind of the end game. So imagine we've ranked students for admission, and we want to decide who to actually admit. All right? And then I'll go back to actually what's the harder problem of ranking the students. So put your consulting hats on. I'm going to pepper you with a couple of questions here. So to set the stage, so the class coming in last fall, right? So those who were admitted or applying for SDSU for admission in fall 2025, we received over 95,000 applications. And these are only first-year students, right? Not transfer students. And we wound up enrolling about 7,000. Okay? So the question is, we have almost 100,000 applications. How many do we admit? And the first question I'll ask you is, should we just admit 7,000 and be done with it? No. All right, good. So a lot of shaking head, right? We're competing. A lot of these students are not going to come, right? But then the question is, how do we decide? Is it 8,000, 9,000, 10,000? All right? So what I want you to think about is, how do we set this up as a predictive model? How do we set it up as a machine learning model? What is our output? What am I trying to predict here? Anyone? Yield. Yeah, exactly. This is actually an easy problem. Thank you. Is a student going to come or not? All right? We have historical records of applications, right? And who wound up coming and who wound up not. Okay? This is called the binary outcome. If you come, right, if you enroll, it's a 1. If you don't enroll, it's a 0. All right? Now, we need inputs. What are we going to use to predict whether a student, right? We don't know if they're going to come. So we base it on historical records, and then a student who applies for fall 2025, we predict whether we think they're going to enroll or not. What are we going to use as inputs for that model? What do you think? What would you use? Or what kind of things? Location, that's a good one, right? Where does the student live? And that's pretty, obviously, AVP Sonia Lord, probably Lord knows, right? We have local, yeah, I'm sorry. But we cater towards our local area, right? So it really depends on whether you live locally, which is south of the 56, or north of the 56, or international, though I don't think well, anyway. What else? GPA. What was that? GPA. Yes. SAT, which I'm going to talk about in the next slide. Yeah, excellent. So since Professor Shen mentioned that, I'm listing some variables that we're going to use in our admission model. But we have the transcript of these kids, right? So high school GPA for sure, but also subject-specific GPA, right? So how they performed in different subjects. Also, we found very useful is how many courses did they take in the different subjects, right? And the last thing on the bottom here is also we realized college courses. A lot of the high school students are now taking college courses, right, at their high school or at a community college or even coming up here for summer courses, right? And so how many college courses have they had, all right? And so we use these as inputs to predict whether the student will enroll or not. And this is called yield rate modeling or show rate modeling. Is Dr. Shao here? Did she come? Yes, Lucy. All right, so Dr. Shao developed this model. She was a data scientist in our institutional research office before leaving for a PhD. And she just finished her PhD at UCSD in biostats, so congrats, Lucy. Sorry, I had to embarrass you. So this is a predictive modeling task, right? We're trying to predict, will a student enroll or not? It's a classification problem, right? 0, 1, either not enroll or enroll. And we could use a regression model, but it's a little different than the regression model I showed you because that's aimed at what's called a continuous response, right? Namely, final exam score, here it's 0, 1. But there's an extension called logistic regression. All right, so we could fit logistic regression. And just to show you how this works, we actually predict the probability that a student will enroll at SDSU. All right, so this example I have here, imagine we want to enroll 100 students. What you do is you rank them for admission, which I'll show you how we do in the next slide. And then you add up, you estimate the probability they'll enroll. You add them all up. These are on a 0 to 100 scale, right, because they're percentages. So you take the sum, divide by 100. Once that reaches 100, you're done. All right, and so in this little toy example, it turns out that you need to enroll 400 students to get an expected or predicted enrollment of about 100. Okay? Now, Dr. Shao's work in her paper actually found, and this is common knowledge in the literature, logistic regression is neat. I can actually show you interpretations similar to the graphic I showed earlier, but it doesn't do the greatest job at predicting these probabilities. All right, we want to get these as accurate as possible. So what we do, or what Dr. Shao did, is ensemble learning. Basically fit a whole series of machine learning models, some of which are going to be better at predicting this enrollment rate for different subgroups of students. Then you figure out a way to combine all those predictions, and you actually get a better predicted probability. Okay? All right, let's skip all that. All right, now we have admission modeling. So how do you rank the students? Before COVID, the CSU used what's called an eligibility index. And it was SAT score plus 800 times high school GPA. And I'm not going to talk about why 800. That's also in Dr. Shao's paper. But what I want to focus on is, come COVID, a lot of universities across the country, including the CSU, decided not to use standardized tests for admission purposes. Okay? So the university came to us and said, geez, we can't admit students just based on high school GPA. What do we do? Okay? So that's my question to you. Think again in terms of a predictive model, right? So I want to build up a machine learning model and predict some kind of performance metric on these students so I can rank them. What would you use as a performance metric? Extracurricular activities. That's an interesting one, actually. But yeah, okay, that's good. What else? And let me give you a hint. So I like that. We have historical data. So we have decades and decades of students who were admitted to SDSU, came to SDSU, went through SDSU. All right? So what data on SDSU would you use to predict students who are coming in? What was that? Time to graduation, yes. What was the other one? Anyone else think? I think? Time to graduation is good. What we ultimately wound up using was just whether they graduate or not. And actually, I had that in my slide because that introduces survival analysis, which is another aspect, but I wound up getting too long. But yes, and I'll jump to the chase here. We just looked at graduation rate because, again, we have students who were applied, came to SDSU, and then graduated or not. All right? So it's, again, a classification problem, right? Do we predict a student to graduate or not based on their application data? Okay, so again, it's still using the same inputs. GPAs in different coursework, number of courses they took, number of college courses, et cetera. So it's still a classification problem. We're still going to estimate the probability that they graduate. Okay, and then we rank them that way. I'm arguing that this is actually an attribution problem. Of course, prediction is important. We want to predict what's the graduation rate. But at this stage, right, we're building up our models. We were trying to determine which inputs best predict graduation success. All right, so this is an attribution problem. All right, and it's proprietary, so I can't share the model with you, but I'll do a little bit of bragging. Just before this, the CSU came out with this GI 2025, the Graduation Initiative, where they were trying to motivate CSU campuses to improve 4-year, 5-year, 6-year graduation rate. And so it turns out we have a benchmark now. So the first class that was admitted using our admission model came in fall 2021. So this past May, we have a 4-year graduation rate, right? May 2025, and it turns out we set a record. All right, so 62.2% of the students graduated. Now, I'm not saying this admission model solved all our student success problems, right? During this time, after the graduation initiative, SDSU had a lot of student success initiatives, and I'll talk about that a little bit later. The bigger thing, and AVP Stronach's in the crowd, we were worried, right? We had this brand new admission modeling. What kind of class are we going to get? How strong are they going to be? And it turned out that they were quite strong. And then this May, we're going to get another set of benchmarks. It'll be the 5-year graduation rate for this 2021 incoming class, and then a 4-year graduation rate for the 2022 incoming class. So we can continue to evaluate it and perhaps refine it. But so far, so good.
What was the percentage before?
Oh, Jeannie, what was the percentage before? Was it 40s, 30s? It was 39%, yeah. And this was years ago. Yeah, and 62 sounds bad. So I'll say, just to put us in good light, we had a really good 6-year graduation rate. I think we were the best, right, among the CSUs. But our 4-year graduation rate was low. So this is a major achievement. And you know, I'm expecting it to get better and better. But yeah, thank you. That's a good question. Okay. Most of my research over my career has been collaborative. So I've already kind of highlighted some of the collaborations I had. So a lot of my work in learning analytics is with our Institutional Research Office, Analytic Studies and Institutional Research, ASER. So again, AVP Stronach is in the crowd. We have a bunch of our institutional researchers here, so thank you all. Dr. Guarcello is the director of our PICA, Program Evaluation Compliance and Assessment Group. So we work very closely with her, so thank you, Maureen. And so the big thing here to me is that our students are now working. They have hands-on kind of data science training working in these offices, right? So our master's and PhD students have desks working aside Dr. Guarcello, AVP Stronach, the institutional researchers, right? Sharing their findings with higher administration. So to me, this is just ideal training, right? So they're sitting at the desks with campus student success leaders, right? Sharing findings, bouncing around strategy ideas. So to me, this is just ideal training in statistical problem solving and communication, all right? So a lot of our work involves developing visualizations for the end user. And what I'm showing here is actually a suite of interactive dashboards that our Institutional Research Office has developed and put out, which allows our campus student success leaders to do exploratory data analysis, right? To study patterns and trends in their student data, get student success metrics from their programs. So what I'm going to do is talk about 2 projects that I was intimately involved in. One is an interactive dashboard, so it's a visualization. The other is going to be talking a little bit more about some of the machine learning methods that we had to develop to study student success programs. And in fact, I'll focus on the Math and Science Learning Center. So I've kind of foreshadowed that. All right, so let's start with this guy. So this is a STEM migration flow part. So the motivation here, so we have former Dean Malloy of Sciences and Dean Roberts from Sciences. I think Dean Alevsky is here. But anyway, the deans and yes, the deans and advisors are concerned, interested in attracting students to STEM programs. So STEM is science, technology, engineering, and mathematics. Attracting students to STEM programs and retaining them, right, so that they graduate in STEM programs. So this is work by Dr. Anna He. Where did Anna go? Anna He. So she developed this dashboard and prototyped it. And then we worked with Arthur Pasternak, who's here today, who unfortunately left us for UCSD. But he then put together this really nice Tableau dashboard. It's a Sankey horizontal flow charts. So I have a video of this. Let me show you. And I noticed on my laptop, it didn't come out too well. I think you'll be able to, you can't really see the wording that well, but you'll be able to see. So the idea here is I'm going to just focus on biology. We can look at students who are coming into the biology major and then see where they graduated from, right? And so some students obviously will graduate in biology. Others will leave biology but still graduate in STEM. And then others will leave STEM but still graduate. And then unfortunately, we also have this group of students who do not graduate. And so we can click on the other side and see, all right, those who didn't graduate, where did they come from? Or what major did they start in? Those who left STEM, where did they come from? All right. So again, advisors can look at this flow, students coming into their program and perhaps leaving, and where did they go to, and vice versa. And this is not just limited to STEM programs, right? In fact, this is our public-facing dashboard, right, which is divided up by college, and then password protected. So behind the firewall, program advisors can look at flow into and out of their individual majors, right? And so the same game, you know, who's coming in, how many are coming in, where do they graduate from, or vice versa. If they graduate elsewhere, where did they come from? All right, so I think this is a really neat advising tool, just to see how students are flowing into and out of various majors. All right, the other big part of our work is in looking at student success programs. All right, and so what I'm going to focus on, I kind of foreshadowed this already, is our Math and Science Learning Center. All right, and the impact of the Math and Science Learning Center on success in our large enrollment elementary stat course. All right, and the game really is characterizing successful students. All right, and one big part of that is what's the effect of the Learning Center on certain subgroups of students. So I mentioned we have this course that's dedicated to business students. Right, so how well do business students perform if they go to the Learning Center? We're always worried about commuters because they obviously spend less time on campus than those who live in the dorms. Right, so perhaps this Math and Science Learning Center is not only time on task, but an opportunity for them to collaborate with other students and the TAs. Right, so how much better might they perform? And really it comes down to a dose-response relationship. Right, who would benefit, which student would benefit going to the Math and Science Learning Center, and how often should they be going? All right, and so this is getting at what's called a treatment effect. Right, so how much better would a student do, or worse, if they went to the Learning Center? And the point here is that any student either goes to the Learning Center or doesn't. Right, so there's always this issue that if a student doesn't go to the Learning Center, we still want to estimate how much better would they have done if they went to the Learning Center. All right, so that's one problem. The second problem is we cannot run a randomized controlled trial. Right, so for example, that's what was done to assess the efficacy of the COVID vaccines. Right, you take a group of patients, you randomly give half of them the treatment, half of them the control. The idea is you're trying to balance the two groups for risk factors, right? So risk factors such as weight, alcohol use, smoking status, location, right, where they live. And the idea is that when randomization mechanism hopefully balances the two groups among all the risk factors to the point that any differences you see in disease progression, you can attribute to the treatment. All right? The problem here is I cannot sit there flipping a coin and say, heads, you go to the Learning Center, tails, you don't. Right? It's unethical. Right? The Institutional Review Board would never approve that. So This is called the quasi-experimental or observational study. And the bottom line here is that the classical statistical techniques will not work for estimating a treatment effect in this problem. So we had to develop our own machine learning techniques for quantifying a treatment effect. So that's what I'm going to show you. All right, so I decided to focus on decision trees and random forest for two reasons. One, it works really well. And this is also Dr. Her's work. So she has a paper, and it's known in the literature also, but she showed that these decision trees and the random forest work really well in learning analytics problems. And I should say a little bit more. So if you were to ask me what is the best machine learning technique, there really isn't one, right? It depends on the data, it depends on the problem, depends on what you're trying to draw inferences on. But we found that random forest is competitive. All right. The second reason is that, hopefully I can get this across, random forest is complicated, right? The method is complicated, the algorithm is complicated, but I think conceptually I can get the idea across. So I thought this might be a good way to introduce a more advanced and kind of modern machine learning tool to you all. I'm noticing that I tried to be clever and use student colors, and it didn't really come out well, but hopefully you can see shapes. All right, so this work started off with Dr. Josh Beamer, who actually is our poster child for collaboration. So he started off in Dr. Guarcello's lab, I think as a master's student, right? Were you there? And then as a PhD student, he worked in AVP Stronach's institutional research office. So he's kind of our example of working as a student and all over the place. His work actually was more aimed at using ensemble learning, like I mentioned for Dr. Shao's work, where he fit many different machine learning models and tried to figure out a way to combine them to get a treatment effect. But what we realized from that work is that the random forest works really well and was hard. So it actually led to a handful of master's and PhD dissertations, a little bit of which I'm going to talk about now. So anyway, with all that, focus on, if you can see it, hopefully, this oval circle and these rectangles. These are decision nodes, all right? And they're all characterized by an input and a cut point, all right? And so the idea here is, with the decision tree, you're trying to split students into two groups. So for example, in this first decision node, I'm splitting students according to quiz 0, which is our algebra assessment. And if they score below a 77.9%, we send them left. Otherwise, we send them right. Okay? And then as you send them down the tree, those students who collect here, we're splitting on high school GPA. Right? If the high school GPA is below a 3.885, we send them left. Otherwise, we send them right. And you keep splitting, keep splitting, keep splitting until you collect them in these circles, which are called terminal nodes. And so I don't know if you could see it, but this terminal node has 172 students, average final exam score 195. So we can now do prediction. If I send a new student down this tree and they wind up falling in this terminal node, we can predict that they would score, based on your baseline early semester metrics, a 195 on the final exam. Or what we typically do is called amalgamation. We combine these terminal nodes into groups, and we would identify like these two terminal nodes are weaker students, perhaps. These are kind of stronger students. These are kind of middle of the road students. But anyway, you can categorize them into groups, weaker to stronger, and perhaps try to figure out some kind of treatment plan, right, to help them do even better in the intro stat course. Okay? Now, from a machine learning research perspective, the big question is, how do I grow a tree, right? Why am I using quiz 0 as my top-most decision rule, and why 78% as the cut point? So I'll first say that these classification regression trees have been around for a long time. In fact, there's a book in 1985 which explains how to grow a tree optimally. All right? But the point here is that that classical work does not work for us since we have these observational studies. All right? So we had to develop our own method for building up trees and random forest, which I'll talk about next. And there's a lot that goes into it, but I'm going to talk about three primary things. One is we recognize that in order to choose the best decision rule, you want to split students into two groups that are as heterogeneous or different as possible relative to the treatment effect. And it turns out, and we actually mathematically prove this, that that is actually looking at effect modification that I talked about earlier, right? So which decision rule, so which input, which cut point splits the student so that the effect of your treatment is as large as possible, right? Relative to your outcomes. So here, your treatment is attending the learning center, so the impact of the learning center is as much as possible on final exam score or passing the course, okay? So that's the first big development. The second is, again, remember, we have an observational study. Students are actually voluntarily deciding whether to be treated or not effectively, right? Are they going to go to the learning center or not? But what we can do is we can estimate the probability that they would go to the learning center. And that's called the propensity score. All right? And so what we do is we control for that propensity score in our splitting rule, right? Or in deciding the splitting rule. And we showed that that actually works really well for handling observational data and computing a treatment effect, which I'll talk about in the last bullet. But before I do that, the other thing we recognized, and this is common knowledge in the literature as well, these single trees are really neat. And hopefully you kind of understand how they work now. But for predictive purposes, you're better to have a whole forest of trees, right? Many, many different trees. So then the question is, how do I build a forest of trees? Well, we run the bootstrap I mentioned earlier, right? So you resample your data with replacement to mimic the idea of replicating your data over and over again. I could do this hundreds of times. So I'm getting effectively 100 different data sets. I fit a tree for each data set, right? And then I could use that as a forest and compute a treatment effect. And what we do is we ensure that every single terminal node includes students who went to the learning center and those who did not. Every student in the data set is going to appear in exactly one terminal node in every single tree. And so now I can actually average the effect across the trees and get a treatment effect for every single student, okay? So let me show you, how am I doing time-wise? Not bad. Let me show you just a couple of things what we can do with this random forest. All right, so this is the same data that I showed you earlier, frequency distribution of the number of students who attended the Math and Science Learning Center. I've now included pass rates, so you can see students who didn't go to the Learning Center had a lower pass rate, for what that's worth.
So as I mentioned, what we can do is compute what's called an individualized treatment effect. And that is, how much better will each student do if they go to the Learning Center? All right, and here's a small scale example. So these are 3 students with similar performance coming into the course in that they each have an SAT score below 1,000 and each have a high school GPA a little bit below B+. 2 of the students 1 and 10, do not go to the Learning Center, and unfortunately they wound up not passing the course. Student 6 went to the Learning Center almost every week, and they wound up passing the course. And in fact, we can now compute this individualized treatment effect for each number of visits that the student could make to the Learning Center. And it turns out that for each of these, the optimal number of visits is in fact 8 to 11 visits, the same as student 6. Okay, and so now we can do this for every single student. And in fact, what we found out is that every student would have benefited by going to the Learning Center at least once. So this is a group of students who would have benefited by going 1 to 3 times. So maybe that's before each exam or before the final exam. This is a group that sees the greatest bang for the buck, all right? So their pass rate is not that high, 64%. A number of them did not go to the Learning Center, but they would have benefited by going maybe before each exam and perhaps during some of the more challenging weeks during the semester. For example, in this course, we find students struggle when we first introduce inference, such as hypothesis testing, confidence intervals. And then this is a group of students who would have benefited by going to the Learning Center every week or perhaps even more.
So when you submit an NSF grant, a proposal to NSF, oh, there we go. When you submit a proposal to NSF, they always ask you, what's your propagation plan? What are your broader impacts? So basically, how are you going to share your work to the community? So I put this data champions under a propagation plan because I think it's the epitome of a propagation plan. So we ran this before COVID for 3 years. Unfortunately, last year was interrupted by COVID, and we haven't had the budget to do it since, but I'm hoping we bring it back because it was really successful. We had about 11 teams per year, and from all the colleges and a bunch of auxiliary units on campus. Each team had a student success project that they worked on for the year. The CSU graduation initiative came out around this time, so we tried to link the student success projects to the graduation initiative. And what was neat is we had a shared data set that all the data champions worked on. We had a whole lot of training. So we trained them on data security, running surveys, software. So how do you collect data? How do you curate data? How do you visualize data? Communicate, how do you communicate your results? Each team had a data coach. So I was the data coach, Professor Fan was the data coach, Dr. Beamer, Dr. Ho was data coach, Dr. Guarcello, the institutional research analysts, right? And to me, the biggest thing that I saw from day one was just this cross-campus collaboration that this set up. So surprise, surprise, challenges in arts and letters were very similar to what we see in the sciences or in business. And successes, perhaps, that we're seeing in arts and letters, we can learn right in the sciences and maybe export or expand to our student success initiatives in the College of Sciences. So when I talk about this, I always mention this as a win-win-win. You can barely see win-win-win. So this really set up a campus culture of data-informed decision-making, all right? And it wasn't just us. This is definitely a top-down approach. So the Provost's office, for sure, has been a huge advocate of data-informed decision-making. President De La Torre, also huge advocate, and she's quantitative-minded to start with, right? So a big supporter of data-informed decision-making. So we now have this campus culture. This is supposed to be a research talk, so on the research end, we're able to get NSF funding to support our machine learning research and partially support the Data Champions program. We got some funding from the CSU, Chancellor's Office, and Professor Hassenstab is here. So we have a California Learning Lab grant that I'll talk about very briefly in the last slide that we got for this work. We initiated, have been part of a number of learning analytics working groups over the years. And then I'll kind of end with this idea of hands-on research training. I mean, to me, it's just the ideal training in that our students are able to develop learn how to develop machine learning techniques and apply them to this really rich student information database on real-world higher education problems. Okay, all right, good. So last slide, and I'll go through this very quickly. I have a lot going on, moving on beyond learning analytics. I'll highlight 3. So I'm finishing up finally a statistical computing book. I actually gave the whole draft to the publisher earlier this year, and I actually just got back feedback last week. And they said it'll probably be a 6-month process to put it together for publication. So hoping it'll be a stocking stuffer come Christmas time, selling it. We've realized that observational studies are very common in sports. So I have a picture of baseball here. So we just finished a study looking at stolen bases. So it turns out, right, that I cannot go down onto the field and when a guy gets to first base, flip a coin and say, heads go steal, tails don't, right? So these are decisions actually often made now by analytics teams in the front office, if not by coaches or some of the players, but it's an observational study. So we've figured out how to extend our machine learning work to study to analyze observational study in sports data. And so for this one, it's looking at the impact of stolen bases on things like run production, win probability, and so forth. Okay, last thing, the grant I have with Dr. Hassenstab. So we have co-developed the Southern California Consortium for Data Science. And the main goal here is to try to help students transition from community colleges and high schools to the 4-year institutions, CSU, UC, to study data science. So it's a bunch of like-minded data science educators from the community colleges, from the CSUs. UC Santa Barbara is our partner. And so we have discussions on successes in the classroom, challenges. We've developed a common curriculum for Intro to Data Science. We talk about articulation. So how can students use courses they take at the community college and get credit for them for their programs of study? And really, just aiming at trying to help students progress through data science majors and succeed in the data science workforce. Okay, so that's it. Thank you, and I'll field some questions.
Thank you so much for an incredibly informative and engaging presentation and lecture. We really appreciate it. Welcome to the group of elite
Yes.
AWJ distinguished professors. And for the
honored.
of you who are in the room who are past recipients, please stand and be recognized. I know we have several of you in the room. To questions, I want to do a quick thank you to all our nominators for all of these awards. It's really, we can't do this without our engagement from our faculty and support who support each of their colleagues and nominate them for these awards. So thank you to them. And then a big thank you to my team. As you can imagine, it takes a lot of work to put these events together, and this is literally on the heel of our largest student symposium this year with 605 students who participated. So a big shout out to the DRI team for all the work that they've done. So thank you. I guess we'll open it up with questions. Please, anybody who has questions, will pass the microphone around.
Rich, first of all, thank you. That was really
Thank you,
nice
Professor
talk.
Roche.
And I can't think of who could take curriculum management and translate it to Moneyball other than you. I do have a question about the enrollment management.
Sure.
You talked about things like location and stuff. And as I know you're aware, we've got to worry about things like essentially discrimination that happens in machine learning models. And I'm wondering how the teams that you're working with took that into account.
Yeah. So I'll answer it this way and you can follow up. So when you're ranking students, we only use the transcript. So it's performance in courses. There's still an issue there, of course. Once we rank students for enrollment, we want to know if they're going to come or not. And so we use everything because it's not going to change the ranking. It's where do you draw the line. So there we do use other data such as location. Location is critical because we admit students differently if they're local region than not. Okay, yeah.
Did you follow up?
So when you're taking a look at things like the transcript, if you are at a school that does not have the resources, you won't have access to the same types of courses. So I think there's still issues there.
Oh yeah, and there are issues. Yes.
Thank you.
Yeah,
very
Roberts.
much. I want to share what I really enjoyed and valued about your presentation was beginning with the predictions. How can we predict from this group of applicants who is going to be successful? But as an administrator, and I think all of my colleagues share this value, that when we do admit students, we have an obligation to support them and provide them every support that they need to be successful. So for me, the more interesting and really more leading edge aspect of your presentation is how do we look at those students who perform at a higher level, at a better level than we might have predicted, and figure out what are the interventions, who are the instructors, and so on, that lead them to be over the line. Because I think that is really what our obligation is as an institution. Thanks.
Yes, and that's an excellent comment, and for sure we do. So obviously this is meant for a scientific audience, so I can't get into the weeds, but our methods are aimed exactly at that. And these machine learning techniques actually allow us to look at individual risk factors, I'll call them, and identify that. And can I make another comment in response to Professor Roche? It's something that I did want to mention in the talk, but I felt it was running long, and this is kind of kudos to AVP Stronach. So, and I'm sure there's going to be an AI question eventually. So you might look at this and say, all right, we developed a machine learning model to admit students, push a button and let it go. but that it can't work that way, right? And so AVP Stronach has had years of experience. It's an iterative process involving the machine and humans, right? And a lot of it is addressing your issue, right? So how do we deal with schools that don't even offer AP courses, or students don't have access to college courses? And it's a very detailed, time-intensive routine. In fact, our enrollment management office is doing it right now. We have a really good analytics team that starts with this model, but then builds the class, right? And so it's definitely heuristic, right? But it has to be, right? So we don't discriminate. So.
Yeah, hi. I'll just second that and recognize, for example, that the CSU caps the amount of weighting that you can have to limit the impact of disparate access to AP classes. But I'm curious to combine both the comment you made and then another word that was here, the human data analytics component. You mentioned rightly that your model is proprietary and you can't talk about it too much. How do you factor in the increasing ability of students or prospective applicants to do the same work that you're doing to some extent? Because I see it, my daughter's a high school senior.
Okay.
So I know all the different ways that people can gain through a set of admissions data to represent themselves in a different way. If there are instructions on TikTok, for example, on how to position your applications. I mean, what
Well, it's actually worse than that. We have these college prep counselors, and you can pay tens of thousands of dollars for them to build your
the
case.
data is
Yeah.
that it's actually reflecting the individual. And then you have an opportunity where applicants can opt to represent themselves in a way that is incongruous potentially with who they actually are. So how do you factor that human ability to change data or to affect data into any of your work? Because it's a broad question.
Yeah, it is. So Jeannie, you can correct or add on to me. We don't use essays, so our admissions is really based on CSU Apply, right, and the transcript that comes in. So gaming the system for the CSU is more, I'm going to take a lot of science courses because I want to go into a STEM discipline. Or it turns out that we found math is important in business, right? So I'm going to be a business student, so I better take calculus, which is not a common thing. So Jeannie, correct me if I'm wrong, but I think we're actually in good shape. When you start talking about the private schools and then you have generative AI writing essays on top of that, yeah, it's tough. And I don't know, I'm gonna say I don't have a solution. Other than, all the colleges talk about this as being a heuristic process. And they're kind of sweeping a lot under the rug, but it is. I mean, you cannot just build a machine learning model, and just have a number for each student. It's part of it is that does not represent the student, but also it could misrepresent, right? Because they're trying to game the system. So yeah, it's tough. It's tough. Yeah, it's tough. It's tough. And fortunately, we didn't have to deal with that. Yeah, Daniel. So Daniel is one of our graduate students.
I'm doing my thesis with him this semester.
And now he asks the hard question.
I want to thank you for your presentation today, Professor Rich. And I want to ask the question that, so I see you have your models for predicting the student admission into the university. I see you have some factors. So I want to ask, is there any factors that you haven't added that you think might be useful into the model?
Yeah, that's a good question. At this point, I would say no. And we've been using this model, for 4 years now, 5 years now? And there's only so much data that comes into the application. So, but this addresses I mean, it kind of ties into the last speaker's question, how other schools might use this admission model or build up admission model. Yeah, Bill.
This is honor. Wonderful presentation, thank you. And I one thing I noticed, stepping kind of broader picture, is you had that great comment or quotation about statisticians playing in everyone's backyard.
I love that one.
And it raised a question for me, which is I imagine there are more opportunities for collaboration available than opportunities that you take. And
Yes.
thinking about that decision, if you will, how do you think through the principles or the ways of deciding which collaborations to pursue, and how is that how is that shaped by what you've done and where you're headed?
Yeah, wow, that's a really good question. And it's kind of twofold. So one is at the individual, and it's definitely true, right? And statisticians are in need. And NIH these days requires statisticians on grants, right? And definitely on this campus, we don't have enough of us to go around. Fortunately, there are enough quantitative people that I think we're covering things, but I don't know, Vice President might not right, disagree. But anyway, to answer your question, so I have the bad habit of taking on to it. So I love doing this stuff, right? And the reason I got into statistics, well, first it was math. I was a math major as an undergrad, and then I took a stat course and found it was a really neat application of math. And so I went on to statistics. And I just love this idea that I can learn science, right, by studying their data. And I've just been jumping around. So I started off with climate change research, and then I did some work in ophthalmology and in periodontal disease, and then some bioinformatics work and some educational data mining. So a lot of it to me is the interest in the subject. So part of it is being a tenure, well, at one point tenure track, but then a tenured professor, and what projects allow me to kind of either as part of the project or branch off and develop new methodology. So is the data rich enough? So I don't want to just do statistical consulting, right? Where it just uses a t-test or a regression model and fits things. I mean, that can be done by one of our graduate students or a consultant. So I look for projects that have rich data with potential for developing methodology. And then if it's there, again, I have a bad habit of just saying, yep, I'll do it. And then hopefully bring on some students and have a research team work on it. So that's been my approach, and it's worked. And I guess because I haven't been overwhelmed, and maybe because I'm good at multitasking. But yeah, for any of you, I know there's some students in the audience who are going into data science. It's definitely something to think about, and you have to say no. I should also say that's, you all might not realize it, but so we talked about machine learning. This is umbrella, but there's so many little areas. Like Professor Roach mentioned time to graduation. If you're studying time to graduation, that's a different endpoint, right? And it's a different statistical model that's used instead of a binary, right? Whether you graduate or not. And my wife, Professor Fan, is the expert in survival analysis. So if someone came to me with a survival analysis problem, I'm interested, but we have a world expert right there. So, we can send it that way. So I don't know if that answers your question. It's kind of seat of the pants, and I try to take on everything I can because it all sounds cool. But
Well, thank you so much for your lecture, for answering the questions of the audience. We'll have plenty of time during the reception for you to continue to talk to Rich and congratulate him.
Okay,
I also want to mention that for your family and friends that are here, please make sure you take a picture. It happens often that we leave these events and they don't get a family picture, so make sure you do that before you leave as well. But thank you again and congratulations. We really appreciate it.
okay.